Tonight, we're stepping into one of the most basic yet misunderstood features of reality itself: gravity. You live with it every second of your existence. It anchors your body to the surface of this planet. It keeps Earth's atmosphere wrapped tightly around it instead of drifting into space. It guides our planet as it endlessly circles the sun, and on the largest scales imaginable, it controls the motion of galaxies separated by billions of light years. But here's the idea that will completely reshape how you think about the universe. Gravity is not actually a force. It is something far more subtle, far more elegant, and far stranger than anything most of us were ever taught. Before we go deeper, if explorations like this fascinate you, liking the video or subscribing helps this channel grow enormously. Now let's begin the journey toward understanding what gravity truly is. The Newtonian perspective. Think about how gravity is usually explained. You release an object, and it falls downward. From childhood, we're told that Earth pulls objects toward its surface, that gravity drags us down, that the sun's gravity pulls planets into orbit. Most people accept this without question. Schools teach it this way. And for everyday life, it works well enough. But it's incomplete. It's similar to saying the Earth is flat because it appears flat when you're standing on it. That description works locally, but it fails to capture the deeper reality. In 1687, Isaac Newton transformed humanity's understanding of nature by publishing Mathematical Principles of Natural Philosophy, commonly known as the Principia. It remains one of the most influential scientific works ever written. Before Newton, explanations for falling objects and planetary motion were largely philosophical speculation. Newton replaced speculation with precise mathematics. He demonstrated that the same rule causing an apple to fall from a tree also governs the motion of the moon around Earth and Earth around the sun. This was revolutionary. Until then, people believed the heavens followed different laws than the world beneath their feet. Newton unified them. His law of universal gravitation states that every object in the universe attracts every other object. The strength of that attraction depends on two things: how massive the objects are and how far apart they are. Earth pulls strongly on you because it is enormous. You and a pencil across the room also pull on each other gravitationally, but the effect is so weak it's completely imperceptible. How weak is weak? If scientists tried to build a detector sensitive enough to measure the gravitational influence of a single person walking nearby, the device would need arms stretching roughly from our Sun to Saturn, about 10 billion kilometers. Anything smaller would have the signal drowned out by noise at the quantum level. That's why you can easily feel a static shock or a magnet's pull, but never the gravitational attraction of another human standing next to you. On everyday scales, gravity is extraordinarily weak, about 39 orders of magnitude weaker than electromagnetism. This extreme weakness remains one of physics' deepest mysteries. Then there's the inverse square law. Double the distance and gravity becomes 4 times weaker. Triple it, and the strength drops to 1/9. This is why gravity only dominates when enormous masses are involved. Despite this weakness, Newton's equations were astonishingly successful. They predicted planetary motion with incredible accuracy. They explained ocean tides caused by the moon's influence. They showed why distant planets move more slowly around the sun. They even allowed astronomers to discover planets they couldn't see. In the mid-1800s, Uranus didn't move exactly as Newton's equations predicted. Astronomers calculated that another unseen planet must be disturbing its orbit. They aimed their telescopes at the predicted location and discovered Neptune exactly where the mathematics said it would be. The cracks in the foundation. For more than 2 centuries, Newton's laws seemed complete. But cracks appeared. The most famous involved Mercury. Its orbit slowly rotates over time, a motion called precession. Newton's equations predicted most of this rotation, but not all of it. Mercury was shifting by about 43 arcseconds per century more than predicted. A tiny difference, but one that was measurable and real. Scientists searched for explanations. They proposed an undiscovered planet named Vulcan. It didn't exist. They modified equations. Nothing worked. The mystery remained unsolved until 1915. That's when Albert Einstein introduced his general theory of relativity. Einstein's radical reality. Einstein's insight was radical. Gravity is not a force. It is the curvature of space-time. At first, this sounds like meaningless jargon, so let's build the idea carefully. We normally think of space and time as separate. Space has 3 dimensions: forward, backward, left, right, up, down. Time moves only forward, from past to future. They feel fundamentally different. But Einstein showed they are inseparable. Together, they form a single 4-dimensional entity called space-time. Every event happens at a specific place and a specific moment, not just in space or time, but in space-time. And space-time is not rigid. It bends. Mass and energy curve space-time itself. The more mass an object has, the more it distorts the space-time around it. Earth curves space-time slightly. The sun curves it much more. Even your own body curves space-time by an immeasurably small amount. To visualize this, imagine space-time as a stretched fabric. Place a heavy object on it, and the fabric dips. Roll a smaller object nearby, and it follows the curved surface. The object isn't being pulled. It's simply following the straightest possible path available in a curved environment. Similarly, when you drop a ball, it isn't being dragged downward by a force. It's moving along the natural path defined by Earth's curved spacetime. This explains planetary orbits. Planets move straight ahead through curved spacetime, which from our perspective appears as an orbit. They are constantly falling, but always missing. The equivalence principle and time. This also explains weightlessness. Astronauts aboard the International Space Station are still deep within Earth's gravitational field. Gravity there is about 90% as strong as on the ground. They feel weightless because they are in continuous freefall. The station falls toward Earth, but moves sideways fast enough to keep missing it. The astronauts fall at the same rate as the station, so relative to it, they float. You experience the same thing briefly when you jump. For a fraction of a second, you are weightless. Einstein realized something profound. Free fall in a gravitational field feels exactly the same as floating in empty space. This is the equivalence principle. It leads to astonishing consequences. One of them is gravitational time dilation. Time itself runs at different speeds depending on gravity. The stronger the gravitational field, the slower time passes. This has been measured directly. Atomic clocks flown on airplanes tick differently than clocks left on the ground. GPS satellites must correct for this effect, or their navigation would fail within hours. Every time you use GPS, you are relying on Einstein being right. Light is affected too. As light passes near massive objects, its path bends. This gravitational lensing was first observed during a solar eclipse in 1919 and made Einstein famous worldwide. Today, it allows astronomers to map dark matter and observe distant galaxies magnified by massive cosmic lenses. The extremes of gravity. The most extreme examples of curved spacetime are black holes. A black hole forms when a massive star exhausts its fuel and collapses. If the mass is great enough, spacetime becomes so curved that no path leads outward, not even for light. The boundary is called the event horizon. Once crossed, all possible futures point inward. At the center lies a singularity, a point where density and curvature become infinite and our current theories break down. General relativity predicts this but cannot describe what happens there. We likely need a theory of quantum gravity to understand it fully. Black holes are not cosmic vacuum cleaners. From afar, they pull on objects just like any other mass. If our sun were magically replaced by a black hole of equal mass, Earth's orbit would remain unchanged, though we'd freeze without sunlight. Gravity, once thought simple, turns out to shape space, time, light, and destiny itself. It is not a force pulling objects together. It is the geometry of reality.